Modal testing is significant in structural dynamic analysis for investigating the dynamic behavior of structures and determine the modal parameters, specifically the natural frequencies, damping ratios and the mode shapes. The modal parameters can be useful information that can help the engineer to improve the structural design, including automotive structures, aircraft structures, spacecraft, and any other structures. However, it is very difficult to get a good quality of the measurement from the testing, since the results are highly depends on proper experimental setup and correct methods. In this video, the procedures for a complete modal testing of a thin plate structure will be explained briefly. This video acts as a guideline for amateur modal analysts to perform experimental modal analysis. The modal testing involves three main steps. 1. Taking the calibrations and measurements. 2. Analyzing the data acquisitions. 3. Identify the dynamic behavior of the structure. In this video, the impact testing is performed on 2 mm of an aluminium thin plate structure in a free boundary condition. To begin the experiment, a setup measurement is carried out. First, discretize the thin plate structure into several elements and nodes. With adequate number of nodes and element used in measurement can help to improve the accuracy of the results, and to display virtuous mode shapes of the structure in the results simulation. Outline clearly the points of impact on the thin plate structure. Make a sequence list for the node to be measured in order to ease the measuring process. Mount the thin plate structure with desired boundary conditions. In this case, the thin plate structure is hung by rubber bands attached at each edge to simulate free boundary conditions. Other supports that can be used are including strings, springs, and many more depending on the structure itself. A water level is used to make sure the thin plate structure is at the finest horizontal position. Test to see if the thin plate structure is oscillate freely by pressing it down. Freely oscillations are important to avoid any external vibration from the hanging pole introduced to the structure and somehow affect the measurement. This experiment involves using a fixed reference accelerometer, 2 roving accelerometers and a few channel acquisitions attached on the structure. These accelerometers are used to measure the vibration motion. Attach a fixed reference at an active excitation point to measure the motion. An adhesive such as Pedro-wax can be used to attach these accelerometers onto the structure surfaces. Attach another 2 roving accelerometers at the particular node according to the sequence list. Set up the date to acquisition before the impact process begins, in the LMS SCADA's worksheets. The date to acquisition helps to gather the signals from the measurement responses, and digitizing the signals for force response function and presentation of the mode shapes. Build the geometry of the structure into a 3D model, by referring to the nodes and elements marked on the structure. Introduce impact on the thin plate structure at the reference position, by using the impact hammer with plastic tip. Repeat the impact for 10 times for every measurement, to get the average reading of the response measured. Averaging a number of signals should increase the reliability of the measurement. Rove the 2 accelerometers for every measurement according to the sequence list, until all the nodes are measured. It is important to be at the best hand position while knocking the structure to ensure that a good measurement can be obtained. Place the impact hammer properly on the foam sponge, to avoid any quirk to happen to the tips. The measured data will be analyzed by using Leuven measurement system. Data block for post-processing, as soon as every satisfactory measurement is achieved. Each peak observed in the frequency response functions show that there are resonance occurred at that particular frequency. Display the animation of the mode shapes by placing the cursor at peaks in the frequency response functions. These mode shapes represent the behavior of the structures act in particular frequencies. By the end of the project, the natural frequencies and the mode shapes obtained from the experimental work will be compared to the predicted result. Finally, the experiment ends once all the mode shapes is validated.